Longest common subsequence. What's the longest hidden pattern two-string share? Longest common subsequence is a pattern mastery 100 staple and a classic in dynamic programming, beloved by Google, Facebook, and top tech interviewers. This problem tests your ability to break down problems into overlapping sub-problems and optimize with DP, a must-have skill for tough interviews and real-world software challenges. Let's break it down. Given two strings, return the length of their longest subsequence, not substring, that appears in both. A subsequence can skip letters, but the order must stay the same. Now, let's assess. Brute force would try all possible subsequences, exponential time. Dynamic programming is the standard and optimal solution here. By building a DP table where each cell dpij represents the length of the LCS for text 1, I, and text 2, j, we can reuse previous results and solve the problem in OM times n, time and space. Here's the plan. Create a DP table of size, len text 1 plus 1, times, len text 2 plus 1, filled with zeros. For each index I in text 1 and j in text 2. If text 1 I minus 1 is equal to text 2 j minus 1, then set dpij to dpi minus 1 j minus 1 plus 1. Else, set dpij to max dpi minus 1 j and dpij minus 1. The answer is in dp minus 1 minus 1. Approach: recursion with memoization. Time complexity, OM times n. This line defines a class called solution. In Java, every algorithm lives inside a class, so this is simply the container that holds our logic. Brief pause before we step inside. Here we define our main method. It takes two strings as input and returns an integer. That integer will represent the length of the longest common subsequence between the two strings. This line stores the lengths of both strings in variables m and n. Think of these as the boundaries of our problem space. They tell us how far we can go in each string. Now we create a 2D array called memo. This is used for memoization. Each cell will store the result of a subproblem so we don't have to recompute it. This is what helps reduce the time complexity to OM times n. Here we kick off the recursive process. We start comparing both strings from index 0, and we pass along the memo table so results can be reused. This line hands control over to the recursive helper function. This defines the recursive helper method. It compares characters in both strings starting at positions I and j. You can think of this as exploring all possible matching paths between the two strings. This is the base case. If we reach the end of either string, there's nothing left to compare. So the longest common subsequence from this point is 0. Pause here. Every recursion needs a clean stopping point. Before doing any work, we check if we've already solved this subproblem. If a value exists in memo, we return it immediately. This avoids repeated work and is the key to making the algorithm efficient. This condition checks whether the current characters in both strings match. If they do, we know this character can be part of the common subsequence. When the characters match, we count one character toward the subsequence and move forward in both strings. The result is stored in memo so we can reuse it later. If the characters don't match, we try two possibilities. Skip a character from the first string or skip one from the second string. We take the maximum of these two results and store it. This explores all valid paths efficiently. This closes the recursive helper method, and this closes the class. Final wrap-up. And that's how this algorithm works. It first sets up a memo table and base cases, then recursively explores matching and skipping characters while reusing previously computed results. Efficient, simple, and elegant. Test case check. Longest common subsequence, recursion plus memo. Let's test our function using this input. Text 1 equals ABAT and text 2 equals ACE. These strings represent two sequences, and our goal is to find the longest ordered subsequence that appears in both of them. Here's why the solution works. Our recursive function compares characters at positions I, j. If the characters match, we include that character and move diagonally forward. If they don't match, we explore both possibilities, skipping a character from text 1 or from text 2, and take the better result. And that's exactly what our program outputs. 3. The result matches the expected value, confirming that the memoized recursion is functioning correctly. Wrap up. So, our implementation is correct. The algorithm successfully computes the longest common subsequence using recursion with memoization, efficient and accurate. Approach: bottom-up DP table. Time complexity, OM times n. This line defines a class named solution. In Java, all our logic needs a home, and this class acts like the container holding everything related to this problem. Here we define a method called longest common subsequence. It takes two strings as input and returns an integer, the length of their longest common subsequence. This is the main method where all the work happens. This line stores the lengths of the two strings. M represents how long the first string is, and N represents the length of the second string. These values help us size our DP table correctly. Here we create a 2D array called DP. This table will store answers to smaller subproblems. Each cell tells us the length of the longest common subsequence starting from specific positions in both strings. This loop walks through the first string from the end to the beginning. We go backward because each answer depends on future characters, which must already be computed. This nested loop does the same for the second string. Together, these two loops ensure we fill the DP table from the bottom up. Since we loop through all MN combinations, this contributes to the OM times N, time complexity. This line checks whether the current characters from both strings match. Think of it as asking, do these two letters belong together in a common subsequence? If the characters match, we add 1 to the result of the next diagonal cell. This means we found a common character and we extend the subsequence by 1. If the characters don't match, we choose the better of two options, skipping a character from the first string or skipping one from the second. This ensures we always keep the longest possible subsequence. Once the table is fully filled, the top left cell contains the final answer, the length of the longest common subsequence for the full strings. This closes the method definition. And this final brace closes the class. Final wrap-up. And that's how this algorithm works. It first sets up a dynamic programming table to represent all subproblems, then fills it bottom-up by comparing characters and reusing stored results. Efficient, simple, and elegant. Test case check, bottom-up dynamic programming, LCS. Let's test our function using this input. Text1 equals ABAT and text2 equals ACE. These two strings represent sequences of characters, and we want to find the longest subsequence that appears in both strings in the same order. Here's why the solution works. We fill a 2D DP table starting from the bottom right corner, working our way up to DP00. At each position, I, J. If the characters match, we take 1 plus the diagonal value. If they don't, we take the maximum of skipping a character from either string. And that's exactly what our program outputs. 3. This confirms that the bottom-up DP logic is functioning correctly and matches the expected value. Wrap-up. So, our implementation is correct. The algorithm successfully computes the longest common subsequence using a complete DP table, efficient, accurate, and reliable. Longest common subsequence. Let's do a recap. We started by defining the goal. Find the longest sequence of characters that appear in both strings in order, though not necessarily contiguously. It's all about preserving order while skipping unnecessary characters. That's what makes it a subsequence, not a substring. Assess recap. We discussed how brute force would explore every possible combination. Far too slow. Instead, we chose a dynamic programming approach that builds up results from smaller subproblems. By reusing what we've already computed, we reduced an exponential problem down to efficient OM times N time. Structure recap. Our logical plan was to create a DP grid where each cell represents the LCS length for prefixes of the two strings. If the characters match, we extend the sequence. If not, we carry over the best length found so far. The final answer rests in the last cell, simple and elegant. Implement recap. We implemented the logic cleanly and ran it through LeetCode. The code executed without any issues, efficiently computing the correct subsequence length. Check recap. After running our test cases, we confirmed that the solution produced the right results and passed all validations, a solid confirmation that our DP structure worked perfectly. Closing insight. The key takeaway? Dynamic programming isn't just about memorizing patterns, it's about recognizing overlapping subproblems and using structure to turn complexity into clarity. Master this mindset, and you'll start seeing DP problems as puzzles that naturally fit together.